Hello, welcome back to my channel, JBTeguihanon, your engineering and chemistry tutorial. Let's jump into our topic. Of course, we are still in the topic called multiple evaporators and compressor systems. So in this video, we are going to look for this number two, multiple evaporators now at different temperatures with single compressor. Okay, in the first topic we had same temperature but multiple evaporators with single compressors and expansion valve. Here still single compressor but individual expansion valve devices and back pressure valves. Okay, we're going to familiarize ourselves with this system. Let's go there. Okay, and here we go. Here it is, multiple evaporators with or at different temperatures. Okay, single compressor. So the setup will be like this. Suppose you have the uh, three spaces where you want to be refrigerated. Okay, you have a warehouse with this configuration. You have door, door, door. You put your products in there, but in this space here you will have, suppose you have a negative 10 degrees Celsius requirements. In this you have a 10 degrees Celsius requirement. Different products, different temperature requirements. In here you have, shall I say, 5 degrees Celsius requirements. So this setup is best for that. Okay. So what you do, of course, you will have a evaporating pressure one unit to be installed here. You will have a evaporating uh, evaporator unit 2 here, and then you will have evaporating or evaporator 3 located there. Then of course it is connected with the piping. Okay, and it goes to the compressor, then condenser, and then goes back there. Okay, and then of course you have your individual expansion valve. That's gonna be the scenarios. Of course, you have to locate your compressor and your condenser in a safe place. So this is just a sketch for us to be able to understand how it is being installed at site. Okay, so this is the setup, site setup, basically a simple sketch. Of course, here we have now the it's like the same type with the previous one, but in the previous one you have the expansion valve here. It's like one only that controls the pressure of evaporator 1, 2, and 3. But here is different. They have their own expansion valve here, right? So each evaporators have uh, different pressure, yeah. And then you have one compressor. You have still have a suction there, point 0.1. Discharge at point 0.2. You have one compressor, okay, and it goes back to the T junction here. Call it now 4. Of course, this is still 3, 3, 3. So this is 3 to 7, 7 to 8, 3 to 10, 10 to 11. You have your junction here at 9. You have your T junction here at 6. Then goes back to 1.1 where the suction compressor is. Okay, now let's see the pH diagram. So the pH diagram is like this. So this is actually the things that we are focusing on. How to draw the pressure enthalpy diagram, pH diagram. Of course, this is our pressure, this is our enthalpy. So at point 1, you can see that point 1 is here, right? And then as you add work to your compressor, it compresses from 1 to 2, okay? And of course, this is your saturation vapor line, saturated or saturation liquid line here, okay? And your 2 is in superheated region. And of course, we assume the isentropic compression in that point. So from evaporator, uh, sorry, from 1 to 2, and then 2 to 3, still have the same, right? You will reject R as your refrigerant inside the pipe passes from 1 to 2, sorry, 2 to 3 inside the condenser. It will reject heat, and eventually your superheated vapor refrigerant will become saturated liquid at point 3, right? Now from 3, suppose it enters to the T junction here, this point, and it passes through the E3 or expansion valve 3. Just suppose some of it, portion of that passes through E3 because there is a junction 3 here, right? We have a junction here. Then this is the junction in pH diagram or pH diagram. At pressure E3. Okay, from 4 it goes to 5. From 4 passes to evaporator 3, it came out here at 5.5, and then it passes through a back pressure valve 6. Okay, so from 4 it goes to 5, and then enters the back pressure. Back pressure will reduce the pressure to the lowest. And what is the lowest pressure? Of course, the lowest pressure is in your PE1. Okay, in the same manner or in similar way, some of your refrigerant passes here and reach to this junction T, and then some of it will enter to E expansion valve 2, and then here it is. Change the color. You have here it's zero point 0.7. Then suppose you have a refrigerant there, passes to evaporator 2, it reaches to zero point 0.8, right? Here's zero point 0.8, and then from zero point 0.8 it passes through the back pressure, and back pressure will lower the pressure similar to EP or PE1, this one. And then the last junction you have here. So those remaining refrigerant will enter into expansion valve 1, 3 of course, and then passes to expansion valve 1, and then it goes out to 10, and then goes out to 11. There is no more back pressure valve because this is the lowest pressure you have in the system. Why? Because this is the last expansion valve, right? So here it is. Okay, from 10 it goes to 11. Okay, so as you can see, all the evaporators same line from here going down, but the smallest evaporator you have is this one capacity, this line here. Okay, from 10 to 11, right? And then you have a middle because it's longer, so it's bigger capacity than the evaporator 1. The bigger capacity is the evaporator 3 because the enthalpy difference is longer, this much. All right. Okay, and their pressure is different. The PE1 is the lowest pressure. Here is the pressure. PE2 is in the middle, but higher than PE1, lower than PE3. The highest pressure you have is the evaporator 3 or PE3, right? So that's the effect of this scenario here, this scenario. Okay, now the formula is, of course, it's the same. So Q1, Q2, Q3 is equal to the load of evaporators 1, 2, and 3, respectively, in tons of refrigeration or TOR, right? And then your mass is, of course, this comes from your Q1, okay, times 210, which is conversion factor. That is basically M1 if you analyze evaporator 1 times H1 minus H10, right? So that is basically where it comes from. If you want to take M1, then you have this equation. Okay, similar way, you will do that to your M2. But take note, the, you have to see it from the pH chart. They are not the same. Okay, that's the difference between the first system that we have, because they have different temperature, okay, requirements, thereby their enthalpy are now different, and their pressures as well. Okay, and then you do the same. So in this way, your H1 will be will, is expressed in terms of this formula here. So it is now energy balance. Okay, so the condition of the refrigerant after mixing and entering into the compressor is shown in point 1 in figure 6.3b. The enthalpy at this point is this. Okay, so here, yeah. So one now is not in the is not along this line, saturation line. It's outside. It's here. What you have got here is H11. H11 is in saturation line. H8 is in saturation line. H5 is in saturation line or vapor, but H1 is not. So thereby you have to calculate it. The way to calculate is to have the mass balance and energy balance. Okay? And this is the formula. So the work done in the compressor is of course the total mass. Okay, M1 plus M2 plus M3 times the enthalpy H1, H2 minus H1. Similarly, in same manner, we get the power required to drive the compressor. This is actually W divided by 60. Okay, that will be in kilowatt. So your refrigerating effect is the same. The same means similar way, but here you add it individually. you add it individually. Yeah, this is just Q1, Q2, and Q3. Add them up. Okay, you will have this formula as well. Okay, and then RA divided by W. Okay, you will have this. Depending on the given, you have this. If the given is P, power required to drive the compressor. Okay, that's all for now in this video. Thanks for watching. Please subscribe for those of you who have not yet subscribed. JBTeguihanon, Engineering and Chemistry Tutorial. Bye.